Good afternoon, everybody. Welcome to another exciting afternoon of organic chemistry with your host, me, Dr. White. Excuse me, was out yesterday doing battle with Mother Nature, changing the oil on my lawnmower, sharpening the blade, and mowing my lawns, which is about an hour job. I have a big plot right in my houses. All right, I'm going to do a fake second start because I'm going to do the following, which I will take out of the video. If you really like what I'm doing this semester, or if you really don't like what I'm doing this semester, please go to ratemyprofessor.com and post something. Now, if you really like what I'm doing, or if you really don't like what I'm doing, send an email to the Board of Trustees and copy the president, Dr. Sam. Sometime today or tomorrow, I'll send out an email, only no announcement, with those email addresses in case you want to. Now, if you're going to send an email to the Board of Trustees, what I'd highly recommend is one, write it and let it sit for a day and go back and look at it. I do that with anything important I ever write. Two, if you're going to do that, besides telling them I'm either a great professor or really awful, put in examples, or at least one example, what you think. And that's why I'm going to take this out of the video, because it shouldn't be on the internet for the rest of eternity. And with that, we're going to do a false start. 5, 4, 3, 2, 1. Good afternoon, everybody. Welcome to another exciting afternoon of Organic Chemistry, Chem 170, with your host, me, Dr. White. Important information. 1, this Wednesday will be test number 4, that I will do like I've done the other at the end of lecture or after our lab. Really, I'll send out within about 20 minutes an email with the password for the PDF file of that test. Tomorrow, hold on, water break. Sometime tomorrow, I will post test number 4 PDF file so you can download it. And that way you'll be able to take the test. All right, another thing, tonight I'll have my office hour. So if you have any questions, stop by, say hello. And this Wednesday, I don't know if I mentioned it, but I will be beginning a class, and I'll take it out of the video, but beginning a class, I will teach you key things on how to interview. If you're somehow in the future wanting a job, you're going to have to interview it. If you're trying to get in some program or school, a lot of times you'll have to interview it. And a couple of years ago when I started teaching this, I realized students don't know how to interview. All of a sudden, the results they are having was phenomenal. And how do I do that? Well, guess what? I've had to interview for high-level jobs like six-figure salary jobs, where they fly me to like New York or other places, and I learned how to interview. And the other thing is, I've hired people, and I've been on the other side of the desk and saying, oh my God, what are these people thinking? How would I ever hire someone like them? And I don't. And I'll teach you the key skills on Wednesday. Also Wednesday, I'll have a special surprise for you. I'm not going to tell you until Wednesday, and that too I'll cut out of the video. But it reminds me, one of my fraternity brothers, whenever he used the scissors, his mouth would go in unison. Why did I remember that? I don't know. Anyways, I said cut out. All right. Dr. White has a photographic memory, and I have a Star Trek memory. My mind can go where no other mind's gone before. All right. Today's game plan. 1, I will do my world famous review for test number 4. I gotta get that fixed. And then we'll go through the problem set on lipids. Sorry, on carbohydrates. Oh, I had a brain freeze. And then afterward, there's time, we'll start on the last chapter. Have you realized this is the second to last week of lecture? I have to say goodbye to you soon. But anyways, let's get going. If you haven't realized it, this is National Teacher Week. So to help Dr. White, turn on your webcam. And those of you who have it on, thank you. All right, let's get to work. All right, thumbs up, people. You see test number 4. All right. First part, polymers. And I forgot to mention, but last week I talked about what test number 4 will contain. It's in Blackrock School D2L announcement, and you also got an email. Now, you should know what is a polymer. In this chapter, I'm going to ask you to learn some definitions, and I think they're important definitions, which is why I'm asking you to learn that. Don't forget, everything you see here in test 4 review is available as a PDF file in the lecture section of D2L for this course. All right, what is a polymer? A polymer is a macromolecule, macro meaning big, molecule made up of repeating units called monomers. And there are two ways of classifying polymers, one by chemical property, and the other is by a key physical property. And you should know an addition polymer has only one type of monomer used that's used to make up the macromolecule. And you should know examples of that. One is saran wrap is an addition polymer, and car tires, rubber tires are addition polymers. Now, the other type is condensation. And condensation polymers, when you have two or more different types of monomers used in making that polymer. An example of that would be my plastic water bottle, which is a polyester, or if you have a nylon jacket, that's also a condensation polymer. Now, the other type of property is physical property. And there are two types. One is a thermoplastic. And a thermoplastic is a polymer, once formed, can be reheated and reshaped to form a new polymer or substance. And an example of that is my water bottle. And that's a thermoplastic. Now, a thermoset, once formed, cannot be reheated or reshaped. In other words, you can't recycle it. An example of that, let me move this out of the way, would be car tires, urethane foam pillows, or your car seats. They can't be reshaped or recycled. Now, let's talk about fats and oils chapter. And the first thing is, what's a lipid? A lipid is a molecule that comes from plant or animals, something that was once or is alive, and soluble in nonpolar solvent, but not soluble in water. Now, there are two types of lipids. And one is a saponifiable lipid. And saponifiable lipid, also known as fats and oils, yield carboxylate anions of fatty acids in the reaction with base and water, base hydrolysis or alkaline hydrolysis. And a non-saponifiable lipid does not react with base and water. There's no reaction. And I showed you that was the steroids. Now, the saponifiable lipids, fats and oils, what's the difference between a fat and oil? And you should know this. A fat is a solid or semi-solid and is triglyceride at room temperature. A oil is a liquid triglyceride at room temperature. Again, fats and oils. Fat is a solid or semi-solid at room temperature. Oil is a liquid, triglyceride at room temperature. If you don't believe me, go into your kitchen and if you have any olive oil or vegetable oil and it's room temperature, not 20 below in your kitchen or wherever you keep them, it's going to be a liquid. And Dr. White will bet on that. I ever tell you if I say I bet on something, I'll bet you I already know I won. That's the only time I bet. Well, I take that back. Once, a couple of times when I gave talks at a conference in was that Reno, Nevada, where it was in a casino hotel, the MGM Grand. I went to the crab tables. Ooh, I was good at it too. Except ever since then, I've never gone again, even though there are casinos in the Chicagoland area now. All right, continuing on. Now, here is the structure of a general fat or oil. It's a triglyceride, meaning triester. Everybody see the structure on there? Thank you. All right. Now, as I promised, essentially no new reactions since the end of amides and amines. And for test number 3, you learned you took an ester and fats and oil chemists draw this backwards from synthetic organic chemists, otherwise known as fats and oils chemists. Ester, acid, water, you get back the alcohol plus the carboxylic acid you would have used to make that. Also, another name for fats and oil chemists are just oil chemists, as opposed to petroleum chemists, which is the stuff that comes out of the ground we call oil, which is a hydrocarbon and other things. Fats and oils are not. And if we take this triglyceride, react it with acid and water, ester number 1 gives us alcohol plus this carboxylic acid, ester 2, this alcohol, this carboxylic acid, ester 3, this alcohol, this carboxylic acid, and you get glycerin, and you get these 3 carboxylic acids. And because they come from fats and oils, we call these fatty acids, which is short for fatty carboxylic acids. Now, if you take an ester, react it with sodium hydroxide, a base and water, you get back the alcohol you would have used to make that ester, but because the carboxylic acid will react with base, you get the carboxylate anion of the carboxylic acid you would have used to make that ester. So if I have a triglyceride, first ester, this alcohol and this carboxylate anion, second ester, this alcohol and this carboxylate anion, and third ester, this alcohol and this carboxylate anion. So you get glycerin and these carboxylate anions. Ooh, that reminds me, do we have time? Yeah, we have time. Everybody see my whiteboard? This is something interesting. A lot of interesting things have happened in my life. When I went to work for AXO, which was originally called RMAC, there are a couple of chemists and engineers there who helped start the company in the 1930s. And they're near the end of their career. And I got to meet them, know them. One of them, Sid Shapiro, was my mentor. And Ralph Potts, who was also one of the people who did a great job starting it. And I learned stories. One of the interesting stories is in World War II, the company was asked to help make a weapon for the Air Force and the military. And that weapon was napalm. How many of you have heard of napalm? And napalm is a chemical or mixture, really, that's almost like jelly or mayonnaise. I've never handled it, but I've seen pictures of it. And the thing is, once it hits on your skin, it sticks there. Plus, it's as flammable as gasoline. So the Air Force would drop this on the enemy. It would stay on their clothes and everything, and they'd burn and kill them or injure them severely. Well, what was the original napalm made of? It's now a different formulation. And do not try this ever, anywhere, home or elsewhere. Gasoline and water. But you know, gasoline and water don't mix. Like dissolves like, or one's polar, one's nonpolar. So they needed a surfactant to hold the two together. And what they took was palmitic acid, this will never be on a test, and reacted it with sodium hydroxide and water. Now, before I go any further, I'll let you figure out what would be the product of that reaction. Why do that? I got to look up something because I have a brain freeze right now. I was right. I didn't have a brain freeze. All right, time's up. What do we have here? Carboxylic acid based, and you get sodium palmitate. And this surfactant, nonpolar tail, long, and a polar head, help mix gasoline and water together to make the military weapon. And turns out, and I forgot which chemist I met him, was it Ralph Potts or someone else, actually came up with the name. Now, how did napalm get its name? Sodium, Na, and from palmitic acid, palm. And that's how it got its name, napalm. And now you know some living history that Dr. White learned. It's amazing how many things chemistry has gotten into our daily life or military life. And the reason I thought about that was you were making the sodium carboxylate. Now, next thing, this is something I worked at a company that did this to the tune of about 2 to 3 million pounds a week. You take an ester, react with steam. Steam is hot water. Now, there are two ways of catalyzing, or actually more than two ways, but two main ways of catalyzing a reaction. What does a catalyst do? Make the reaction go faster. In industry, time is money. So the faster you can make it. Now, one way is add a catalyst. And for an ester, that's either acid or base, which I just showed you. The other way to catalyze a reaction is increase the reaction temperature. There's a rule of thumb. Oh, wait, it's on this thumb. Can you see it? Is for every 10 degrees C you raise a reaction, the reaction rate doubles. And it's a rule of thumb, which means it's true about 95% of the time. So instead of using acid or base, you use steam, hot water, and you get back the same products you would for acid hydrolysis. Ester, alcohol, and the carboxylic acid you would have used to make that ester. And therefore, if we take steam, first ester, you'll get this hydrox group and this carboxylic acid. Second ester, you'll get this carboxylic. Am I doing fast enough? Oh my God, Dr. White just had a brain freeze. One of you should have told me I already did this. Well, it's good review and I'm finished with it. Let me get back to carbohydrates. All right, who put something in my water bottle? It happens once a semester sometimes, and it just happened. Hold on. I did it. All right, now that you had your spring replay, let's do the right problem set. Oh, wait, what am I doing? I just had a total mind breakdown. See what happens when you mow your lawn on a Sunday? I think it's time for me to retire. Not. All right, let's get back to it. I thought I was doing the review. I mean, the problem set, and I was going to do problem, but we're doing the review. And here we have steam making the three esters and glycerin. See what happens when you don't get enough sleep? Bad, Dr. White. All right, you should know the structures of stearic acid and oleic acid. Both have 18 carbons. Here is the tail is all carbon-carbon single bonds. So does not have any double bonds in it. And oleic acid has a double bond. This is at C9, and you have carbonyl, carboxylic acid, 7 carbon CH2 double bond, 7 carbon CH2 CH3. And stearic acid is comes from saturated fats. And you should know a saturated fat, just like saturated hydrocarbon, only has carbon-carbon single bonds. Now, if you put down only single bonds, I'm going to mark that wrong because the ester has a carbonyl, which is not a single bond. And what's an unsaturated fat? That's a molecule that has at least one carbon-carbon double bond in the fat or oil. All right, things you should know. Tallow, beef fat. White grease, yellow grease, pig's fat. And to give you that real world feeling of working with fats and oils, which I did, tallow, white grease, and yellow grease, I've shown you this representation, which works well. Tallow has a sterile, which is, if we look at it, and here we have an oleal group, and R sub S is another sterile. And what I mean by that is and this is what I mean by R sub S, because this plus this, which is this part, when you hydrolyze the ester, you get stearic acid. And for this part right here, you'll get, this is what I mean by R sub O. And when you take this plus this from this part of the ester and you hydrolyze it, you'll get oleic acid. Now, I'll never ask you to draw it out like this, but you should know the structure of oleic and stearic acid. And therefore, if on a test I were to ask you, and in real life, tallow plus sodium hydroxide and water, what are the three products? In reality, what I'm really asking you is this right here reacting with sodium hydroxide and water. And the first ester gives this alcohol plus sodium stearate. Second ester gives this alcohol plus sodium oleate. And the third one gives this alcohol plus sodium stearate. If I ask all the products, you just have to do this, this, this. You don't have to put two there because, as you know, organic chemists don't balance equations unless you have to. And as soon as this goes away from the bottom of the screen, you should know, let me rewrite it on the whiteboard. You should also know, if I put down tallow or white grease or yellow grease and base and water, you should know the reaction products of that. We did that already. And same thing, tallow, white grease or yellow grease. You should know what's the products for this reaction with steam. And this both would be glycerin. This would be sodium oleate and sodium stearate. This would be oleic acid, stearic acid, and glycerin. All right, one of the most important things I'll teach you this semester, everybody get the message? Thank you. How soap works. You should know, first of all, what's the structure of soap? Non-polar tail, polar head. Soap, non-polar tail, polar head. When you clean something, you're going to use water. Well, water is polar. And the dirt and grease you're trying to get off, whatever you're trying to clean, is non-polar. And you should know the most important piece of this puzzle is light dissolves light. Something that's polar is soluble in polar things, something that's non-polar, soluble in non-polar things. You mix the two together, they're not soluble. We did a lab on that. And just go look at a bottle of oil, vinegar, red dressing. And because light dissolves light, the nonpolar tail of soap is attracted to the dirt. And there's more than one molecule used when you wash your hands. And this forms a micelle. And you should know how to draw the structure of micelle. And now, while you're washing your hands with soap and water to get the dirt off it, you form micelles, and water looks at the micelle and says, oh, and only sees the polar heads on the outside surrounding the dirt particle, says, oh, micelle, I'm polar, you're polar, let's go down the drain together. And they do. Now, in terms of steroids, you should know how to draw the ring skeleton for all steroids, otherwise known as hormones. Everybody see my whiteboard? Thank you. And let's do one. 6-membered ring. Next door on the right is another fused 6-member ring. And then at 12 o'clock high, this carbon right here, there's another fused 6-membered ring. Oh, that looks awful. I'm going to do this again. And a 5-member ring. Let's try it again. And then next door, that third 6-member ring is a 5-member ring. And you should know how to draw the ring skeleton of a steroid. And if yours doesn't look as pretty as mine, or if yours looks better than mine, that's okay, as long as I can interpret it being right. Now, next I talked about carbohydrates. And what is a carbohydrate? You should know the definition is a carbohydrate is a polyhydroxyaldehyde or polyhydroxyl ketone, poly meaning many, or a molecule that upon hydrolysis, adding water, becomes a polyhydroxyl aldehyde or ketone. And sometimes when you do that hydrolysis, like in your stomach, you need acid catalyst. Now, at this point, I talked about a concept dealing with all molecules, but especially important with carbohydrates. And that's chirality. And you should know what is chirality. That's Greek for handedness. Now, when we talk about chirality, we can talk about objects such as your shoes, your gloves, whatever, and molecules too. And there are two types of objects. One is chiral object, and the other is achiral object. A means without. That's the prefix. So chiral object is an object with a non-superimposable mirror image. I hope you all did put your hands up to mirror to find out Dr. White wasn't lying to you. Your hands are chiral, which is why I got the Greek name for handedness. Aren't you glad they didn't pick the Greek word for footedness? Nah, they picked the right one. Now, achiral object, no handedness, is an object with a superimposable mirror image. And later today, if Dr. White's mind doesn't go out my ears, we'll do the carbohydrates problem set. Now, when we look at molecules, especially organic chemistry, which that's what this course is, we have chiral carbons. And a chiral carbon are carbon atoms with 4 different groups or 4 different atoms or a combination of 4 different groups and atoms. Now, I'll never ask you what's a chiral carbon, just like I won't ask you what's a chiral or achiral object, but I will ask you to know how to identify that. And later today, we'll go through some examples in the problem set. Whoop. Let's move this up here. Another thing you should know, not the definition, but how to draw, is an enantiomer. An enantiomer is a non-superimposable mirror image of a molecule. And we'll do that in the practice problems later today too. Now, when you start with glucose, we have an alcohol here on C5, aldehyde up here, and this is something you should know. In test number 2, you learned aldehyde or ketone plus an alcohol as the catalyst, you get a hemiacetal or hemiketal. Now, when the 2 functional groups are in the same molecule, a lot of times, in this case, you don't need a catalyst, and you have this equilibrium. This hydroxyl group attacks this carbonyl carbon, like this hydroxyl group, and this oxygen-carbon bond is this one right here, and you form this. And if on a test I give you the starting material and equilibrium, you should know how to draw this. If I give you the product equilibrium, you should know how to go back to glucose. I will never ask on a test what's the structure of glucose, or the next one, fructose. And the same reaction that you should know for fructose is this hydroxyl group will attack, which is an alcohol, this carbonyl ketone to form this hemiketal. And the same thing, you should know this goes to this. And if I ask you what's the starting material, it's fructose, which has the structure. Again, on the test, I will never ask you to draw the structure of fructose and glucose as a nomenclature problem, but this one is not nomenclature, it's reaction. Now, there was a slight wrinkle on a reaction you learned for test number 2, which I taught you, and that is you take a hemiacetal or ketal and react it with a separate alcohol and acid, you'll get an unsymmetrical acetal or ketal. That means the R groups on the oxygens, which you learned in test 2, are the same because you reacted with 2 moles of the same alcohol. Here we're doing separate. So if I take this, which is the glucose side of glucose, I have this molecule here is a hemiacetal alcohol and acid. I'll replace the hydrox group with OR triple prime. And why is this important? Because that's how starches are made and sugars. You should know sucrose, table sugar. It's made up of fructose and glucose bonded together. You should know starch is polyglucose molecule or polymer, many glucose molecules. So if I react a lot of glucose molecules together with acid, I will make starch. What's the linkage? I won't ask you to draw it, but you should know that's an acetal or ketal. In starch, it's really acetal. And for sucrose, if you take acid and water, which is what's in your stomach, I still think it's one of the great miracles of life in my mind that in my stomach and yours too, you have cells that synthesize hydrochloric acid. Oh, wow, this is amazing. I find it amazing. And that acid and water helps break down your food. So if you take sucrose and react it with acid water, you get glucose and fructose. Starch is a polymer of glucose with acetal linkages, acid and water, you get back glucose, which is why this is the most abundant sugar in nature, because we and animals, when we consume starch, make glucose, which is what our blood transports throughout our body. Now, I asked you to learn how to describe with words and a general reaction what happens when you eat a fat or oil. What's the functional group in a fat or oil? Ester. And therefore, in your stomach, there's acid water, so it's acid hydrolysis of an ester. Next, here's the general reaction. Ester, acid, H plus, you can, or you could put HCl, either one works for me, plus water. Three more rings, two more. Someone I don't know, and I'm not going to answer it. You see it? Oh, by the way, I have caller ID, and it wasn't the president or a speaker of the House of Representatives. I don't even know their phone numbers, but it was a Chicagoland phone, so robocall. Anyways, back to chemistry. When you eat a fat or oil, what happens in your stomach? Acid hydrolysis of an ester. The general formula, which you learned for test 3, ester, acid, water, you get back the carboxylic acid, the alcohol you would have used to make that ester. Next, you should know how to describe with words and a general reaction what happens in your stomach when you eat a carbohydrate. And a carbohydrate, what's the functional group that holds glycerin, wrong molecule, glucose together in a carbohydrate? And that is an acetal. And in your stomach, acid and water, acid hydrolysis, functional group acetal. And for test number 2, as soon as it disappears, there it goes. If you have an acetal, react it with acid and water, you get back the aldehyde or ketone you would have used to get that acetal or ketal plus the alcohol. If you want to put 2 there, you can. You don't have to. And with that, I'm done with the review for test number 4, assuming I don't have another meltdown in my brain. Why, for some reason, I'm looking at it and saying I'm doing the problems because I was doing specific ones. And what am I doing this? Reboot. All right, any questions? All right. Did I tell you? I think I already told you about how to use a proper drain cleaner. I talked about hair and grease removal. Did I talk about how to clean your bathtub with Barkeeper's Friend? I think I did. Did I do that? Anybody? Yep, I got some. All right, so I'm not going to do that. But I'll do a quick thing. If you go to your local big box store, and let's go to our local big box store, home improvement big box store. I don't get any kickbacks from them. Everybody see Home Depot on your screen? Probably not, because I didn't do this. Now do you see Home Depot? Everybody? If we put in lithium grease, you'll see a bunch of these products. And Dr. White uses both this and this Lucas lithium grease. Now, if you know your chemistry, you know alkali metals, especially lithium, potassium, and sodium, and lithium is a good one, will burn in air. Well, how can they put that in grease and it doesn't burn? Well, what they really mean is this. Various fatty acids, and I'll let you do that general equation. What would be the general product or product if I take a carboxylic acid, react it with lithium hydroxide and water? I should warn you, the lab on Wednesday, be careful, it's real fattening. It's going to be carbohydrates. Yeah, I'm going to tell you a cute little story that happened in the lab a couple of years ago. Real funny, actually. All right, anybody need more time? Thumbs up, people. If you're done, give me a thumbs up. All right, let's go ahead and do this. What do we have for test number 3? You have MOH, lithium, sodium, or potassium hydroxide. That's a base. And you'll get the carboxylate anion. In this case, what you get is this. And this is called the lithium grease or soap. Now, as I taught you, bar soap is this. And when you change the sodium, how many of you have ever touched a bar of soap? I hope most of you have. It's slippery. It's a good, and if you've ever done woodworking, it's a good lubricant when two types of wood are stuck together, like in a drawer. You can also use other things too, beeswax. But anyways, when you do a lithium carboxylate of a fatty acid, this is really good lubricant. And it works good on the rollers in my garage door and a few other things around my house. And they came up with that about 10, 15 years ago and been doing it ever since. Let's see something. Nope, they don't give the, I was looking for, they give the, let's do one more thing. I haven't done this. Well, I only even got one named after me, white lithium grease. You guys see Google on your screen now? Let's just do, and look what's up there. Usually this is from uh, oleic acid, sodium, lithium oleate. And also they have where you have a hydroxyl group. That's not what they're showing in the picture, but it's your long R group. And that's what it mainly is, or also known as lithium soap. But you know, organic chemistry is all around you. Anyways, I thought I'd show you that. All right, any questions about test number 4 material? I'm going to give you an extra long break today. Don't tell the dean. Why don't you come back at 1:55 and I'm going to go stretch and check my mail too. I'll see you in about 5.5 minutes. Let's get back to work. But you didn't realize all the organic chemistry going on in Home Depot and other places. It's there. All right, everybody back? Let's get going. No, I'll do the right one. Don't tell anybody about my brain freeze. Shh. All right, let's let everybody see the carbohydrate practice problems on your screen. Thank you. All right, Dr. White got lazy at the end of the semester, near the end. And what is a carbohydrate? That's a polyhydroxyl ketone, polyhydroxyaldehyde, that or a molecule upon hydrolysis forms a polyhydroxyl ketone or polyhydroxyl aldehyde. Is each of the following items chiral or achiral? And how do you do that? Well, you look, does it have a superimposable or non-superimposable mirror image? I'll give you a secret. If in the item you're looking at has the word right or left, it's always going to be chiral. So if I look at the following, a left foot has the word left, it's chiral. But if you don't believe me, next time you're in front of a mirror, hold your left foot up and you'll see your right foot, and take your right and left feet. And I'm not going to do it for you. No, I'm not going to show you my feet. You have socks and shoes on. But anyways, they're not superimposable like your hands. So your feet are chiral. All right, a mitten. Uh-oh, it's time to do how bad can Dr. White draw? And if you have a mitten with no leather palms, by the way, it's permitted to laugh your head off now, a mitten. If I draw my mirror image, sorta, these are superimposable. So if it's superimposable mirror image, a mitten is achiral. And I'm not going to ruin your day by showing his tube sock with no writing design. And I should have also put there no toes. Some of you have seen tube socks for women who have toes on them, but they're also achiral. And a sewing needle, and I think I did that in class, has a superimposable mirror image, sew with a piece of rice. Now, a baseball glove, and this one, remember there's left or right baseball gloves. So baseball gloves are chiral. And I think we did in class, remember Simon Says, didn't we play Dr. White Says? And I said, touch your right cheek. Well, if you knew your right from your left cheek, that means your face is chiral. And finally, I think I did the picture of a car, and hopefully all of you had a good laugh. And a car is also chiral. It has a non-superimposable mirror image. Just think about it. If you're at the front of a car and somebody says, please get in on the right side, you would know right from left in a car, which also tells you it's chiral. Now, number 3, circle the chiral carbons in the following molecules. How do you know if something's chiral? It has 4 different groups, 4 different atoms, or a combination of 4 different groups and atoms. If it has 2 or more of the same atom or group, it cannot be chiral. If it's in a double or triple bond, it can't be chiral. So if we look at A, 3 hydrogens, that carbon's out, 2, that's out, 3, that's out. This leaves this and this. This carbon has chlorine, hydrogen, methyl group, and these 3 carbons with the hydroxyl and chlorine That's four different things. It's chiral. Same thing here. Chlorine, hydroxyl group, methyl. This is our group with three carbons and a chlorine. Four different things. That's why I circle it, chiral. Now, if we look at B, we have, all right, sulfur, we're looking at carbons, so that's out. And three hydrogens, that's out. Two hydrogens. These carbons aren't double bond. They're out. This is the only one to consider. Hydrogen, thiol group. Methyl, this is called the Oleic group, three carbons double bond, which you don't have to learn for my class. And that's, guess what? A chiral carbon, four different groups. I better share the fun. There you go. Circle all the chiral carbons in that molecule. I'm sharing the fun. When you're done, give me a thumbs up. Those of you who don't have your web camera on, you can use your Symboli. Remember, Dr. White's renamed emoji Symboli after symbol. All right, well, some of you haven't found the Symboli button yet, so I'm just going to go ahead and let's do it. All right, if you have two or more of the same atom or group on a carbon, it can't be achiral. So that's out, that's out, that's out, and this is out. If it's a carbon in a double or triple bond, that's out. So we just have these two carbons to consider. And if we look at this carbon right here, it's got a hydrogen, hydroxyl group, methyl group, and this long thing, R. It's four different groups or atoms or combination. Now, if we look at this carbon, as a chlorine, hydrogen, this I'll call R, and this group R prime. These are different. Hydrogen, chlorine, R prime, four different. There you go. Oh, let's do another one. These are fun. And why don't you circle all the chiral carbons in that molecule? Boy, I'm really in a sharing mood this afternoon. Oops, forgot something. I only had 3 bonds to carbon, or it just fell off. I think I better eat more fish and feed my brain. And when you're done, give me a thumbs up. Oh, I see a lot of thumbs. So everybody's done. I better get to work. And the question is, circle the chiral carbons. Ah, it's a carbon in a double bond. It's out. Carbon with two hydrogens is out. Now, each one of these lines intersections is a carbon. Notice this carbon right here has two bromines, so it's out. And we just have this carbon right here, hydroxyl group, hydrogen, this and this. So it has four different groups. Same thing, hydrogen, hydroxyl group, this part and this part, and they're different. I'll call it R and R prime, and therefore that would be out. And that's how you would do it. And if you notice, I also have in a ring. And let's look at this one. Remember, I haven't asked you this in a long time. Everybody, how many bonds to carbon? Anybody have nightmares? How many bonds to carbon? 4 bonds to carbon. Hold on, let me fix that finger. 4 bonds to carbon. And why am I bringing this up? If you look at the ring, this carbon, this carbon, this carbon, and this carbon have CH2. You don't show it, but it's there. This carbon has 3 hydrogen. That's out, this, and this. These are the only 2 carbons. Remember, every bend in a line is a carbon, and this carbon has H, CH3, these 2 carbons, and these 3 carbons with the hydroxyl group, 4 different groups. This carbon has H, OH, and then these 2 carbons and these 3 carbons, actually 4 counting the methyl group, so 4 different carbons, and those would be circled. And we just did one like this already. All right, number 3, draw the enantiomer of the following molecule. Enantiomer is the non-superimposable mirror image. Therefore, I'm asking you to draw the mirror image of this. And remember, you don't have to draw the mirror image of achiral carbons. So aldehyde I have here, hydroxyl group, what's close to the mirror, you draw. First in the reflection, what's farthest away, this hydrogen you do here. And the rest of them are the same. Now, this is an achiral carbon at the very bottom. Now, if you put HOCH2, you could have done that, and I just smile because you don't have to. Now, on a test, I will not give you the 3-dimensional, even though I did show it to you, because I didn't talk about it, so I don't do that. What I can do is make you work. And I would ask you, draw the enantiomer of that molecule. And thumbs up, people, when you're done. Give me a thumbs up. You people without webcams, does your thumb up symbol work? I don't know. All right, let's do this. How do you draw the enantiomer of this molecule? You draw the mirror image. Now, you don't have to, but I like to draw my mirror because it helps me focus on what I'm trying to do. This is an achiral carbon, so you can write it this way. If on a test you would have drew this like this instead of like that, I would mark it correct. And same thing here. If you had drawn it this way, that's fine. There's free rotation around carbon-carbon single bonds like that. Anyways, this is a chiral carbon. Here's one here, here's one here, here's one here. What's close to the mirror? Hydroxyl group. What's farthest away? Hydrogen. And let me put the hydroxyl group closer. And then hydrogen, hydrogen, what's farthest away? Hydroxyl group. Hydroxyl group is close to the mirror. I'll see that first. The reflection farthest away, hydrogen, hydrogen. Farthest away is bromine. And that would be the enantiomer of that product or molecule. All right, given the following molecules, which I won't do on a test, but I thought I'd do it here. I've done something different. You can draw them or you can name them if you want. That will be something different on test number 4. And if we look at the following, glucose and fructose acid, what do you get? Sucrose. A lot of glucose together, what do you get? Starch. Now here, when I did this problem set, I had mastered a curve, so that's why it sort of got square corners. It shouldn't. And if you take a hemiacetal or hemiketal, reacted with a different alcohol and acid, you replace the hydroxyl group with the OR triple prime, and you'll get an unsymmetrical acetal or ketal. And here we have this. The only thing that will change is this up here. And what's our triple prime ethyl? Then I did the chemistry instructor's favorite trick on a test, give you a big, scary R group cyclohexane ring. Hydroxyl group replaced with OR triple prime, and the rest of it stays the same. And the oxygen, and you have this R triple prime cyclohexane ring. Now, as I mentioned earlier, you should know what happens when you eat a carbohydrate. As acid hydrolysis of an acetal, which is this general reaction, you get back the aldehyde or ketone plus the alcohol you would have used to make that. Well, if you take sucrose and consume it, acid and water, what do you get back? Glucose and fructose, which has the alcohol and the aldehyde or ketone in the same molecule. And if you take starch and consume it, you get glucose. And glucose is made, each starch molecule is a polymer glucose. Acetal linkages are broken down and you get back glucose. Now, G, just ignore, that's just a branch starch that I shouldn't have put down there. Bad, Dr. White. And that would be that. Oh no, we're done. Sorta. Now it's time for you to try something out on your own. give the product for the following reaction. Your turn. And when you're done, give me a thumbs up. Oh, wait, I'll try polling. Let's see how you guys do with polling. All right, looks like everybody's done, so I better get to work. And how do you do this reaction? Well, what do we have in here? I have an aldehyde and at C5, carbon number 5, I have an alcohol. And the general reaction is ketone or aldehyde plus an alcohol. Now, if we're intermolecular, separate molecules, you'd need an acid catalyst. This is intermolecular in the same molecule. You don't need the acid catalyst. Keep your eye on the carbonyl carbon because that's where the fun is. And you'll get this hemiacetal or hemiketal. And this hydroxyl group is this one on this alcohol, this carbonyl. Here, what happens? This attacks that. Same thing here. And what do you get? You form this new carbon-oxygen double bond and convert the carbonyl to this hydroxyl group on the hemiacetal. Well, what's not involved in the reaction, I'll just rewrite. Let me do a better job of rewriting it. That's not involved. This hydrogen will stick around. This hydrox group, these hydrogens, these alcohols, this hydrogen. Now, this carbon will still have the hydrogen, but now this oxygen, which is this oxygen, is going to be bonded in the world's ugliest, longest bond, but I've helped you not have to learn Hawthorne structures to make this oxygen carbon double bond. And this carbon here, which is this carbon, you'll also have a hydroxyl group. If that didn't happen, you wouldn't have starches. That's sad. Did I tell you one of the most dangerous starches in my life? Lay's potato chips, the sour cream and onion. Oh, I only buy it a couple times a year because they evaporate immediately. I don't know where they disappear to, my mouth, really. The other thing, bad carbs in the last 2 or 3 years that I've really become fond of, which are quite dangerous and I don't buy too many, are Doritos. The original flavor I like the best. Dangerous stuff. Hold on a second. Dr. White's got a cheat. You can tell I'm not a sugar chemist. Yep, I was right. And by the way, I forgot to tell you something in case you didn't figure this out. This was this is glucose. And now if we do another one, which this is fructose, same question, give the organic product or products are the following. 3 points each. All right, thumbs up, people, if you're done. Show me your thumbs. I haven't done that all semester. I won't do it again. Sorry about that. All right, let's take a look at this. And turns out this is the same reaction of this general reaction up above. And here we have now a ketone, carbonyl. And at C5, we have an alcohol. Because it's intramolecular in the same molecule, we don't need a acid catalyst. So whatever not involved in the reaction, I'm going to rewrite. And that's the beauty of organic chemistry. Now this carbon here is this carbon again, the hydroxyl group or the alcohol attacks it. And therefore, this will attack and bond to that carbon. And what we have, we're making this carbon is now that carbon. What's on there? A hydroxyl group. And this bond right here between this carbon and this OR is this. But before we do that, I better put in the other stuff that I forgot to put in, and now we'll form a carbon-oxygen bond, and that's the product. And fructose, which has a ketone, where glucose has an aldehyde. And with that, part of the review, let's review again. One, you should know how to describe with, I should ask everybody to see my whiteboard. Thank you. How to describe with words and a general reaction when you eat a fat or oil. And what's the functional group in a fat or oil? And that's an ester. And an ester, when you eat it, it goes into your stomach, acid and water, and that's acid hydrolysis of an ester. And here, what's the general reaction? Ester, acid, water, and you get back the carboxylic acid plus the alcohol you would have used to make that ester. And now what happens when you eat a carbohydrate? How do you describe that with words and a general reaction? What's the functional group in starches, carbohydrates? And that's an acetal. And here, when you eat it, chew it, and swallow it, in your stomach, there's acid and water. So that's acid hydrolysis. Of and what functional group? An acetal. And as I taught you for test number 2, and you can use both an acetal or ketal, acid and water, what do we get back? The ketone or aldehyde we would have used to make that acetal or ketal, plus the alcohol. And for those who must, I don't, but I had 2 twins who got, ballistically upset. If I didn't balance things, I now do that with a little 2 so nobody gets really upset. Last thing I need is upset students. That's not nice. I don't want to do that to you. And you should know that. And finally, once more, all right, your turn. I'll let you try it and then I'll do it. How does soap work? And don't forget, draw the structure of soap and talk about my cells. Not your cells, my cells. Oh, that's a bad joke. Sorry. I'm inflicting you to a lot of bad jokes today. I see one person done. When you're done, give me your thumbs up. Everybody done? All right, quick announcement. Remember, this is National Teachers Week. So Wednesday, it's Wednesday. Turn on your webcam for Dr. White Day. So if you have to put on some makeup like I use, no, I don't. Don't forget to use it. And I'll see you on Wednesday on your webcam, please. All right, let's do this. How does soap work? First of all, what is soap? Soap has a nonpolar tail and a polar head. Next, the most important piece of the puzzle, how does soap work? I'll even change colors because soap important. And go to super font. An important piece of the puzzle, how does soap work, is like dissolves like. Things that are polar are soluble in polar things. Things that are nonpolar are soluble in nonpolar things. And water, as you've learned, is polar. It's the most polar substance in the universe. And dirt and grease are nonpolar. Now, if we have a magnified piece of dirt, it's nonpolar, and the soap, nonpolar tail, polar head, looks at dirt. Just how did it get up there? Once in a while, this does weird things. All right, let's write it again here. And the nonpolar tail of the soap is attracted to the dirt, and you're using a lot of molecules of soap, and it totally surrounds it. I'm just going to draw 4, and this, you should know, is a micelle. And micelle looks at dirt, and, or I should say, the micelle is formed with the dirt in the center and the polar heads of salt of the soap all around it. And water looks at a micelle and says, oh, you're polar, I'm polar, like dissolves like, let's go down the drain together. And they do. Any questions on any of that so far? All right, quick commercials from Dr. White. Don't forget, I have my office hour tonight. And if you have any questions, stop on by. I didn't mention earlier, but don't forget, this Wednesday is the deadline for the extra credit project. Yes, 10 extra credit points. And if between now and Wednesday, when it's due, either email it to me, your project, or come to my office hour, and I'll even allow it Wednesday night office hour. If there's something wrong, I'll tell you, and you can fix it. That way, there's no reason you can't get, if you want them, 10 bonus points. It's like having 10 points in the bank or on any extra on any test. It's a good thing. Now, before we take a break, I figure I'd tell you Dr. White's story because we got time. Did I tell you a secret? I cheated this semester. How did I do that? Well, normally during the semester, face to face, whenever I give a test, guess what? I'm not lecturing, but I can get away with giving an overnight test so I can get an extra 4 hours this semester lecturing, which I think is a good thing, which means we'll probably end early today. Shh, don't tell anybody. But did I talk about board and chemical and uh, how to solve problems? Good. I got a quick story for you. And it's a good, you didn't realize it, but I do teach certain things beyond chemistry in my class, and this is one of them. After, I think it was my second year and a half working at AXA, or even less, I had a reputation of being a great problem solver, especially when there are problems in our company's plants. And that happened at the other companies I worked for. I was working for Board and Chemical, which is now called Hexion, and they have a different products they made, and they were trying to close down a plant in uh, a suburb of Milwaukee. I forgot what name of it. Just let's call it outside of Milwaukee. And they were trying to transfer all the products to a plant in Toledo that they wanted to expand, and it was a cost-saving method. Stupid, but they wanted to do it. Nobody asked me. Well, it wasn't an area I was responsible. And the plant made a special product that GM used to make the Saturn engines for their cars. Even though they don't make it now, a number of years ago, Saturn was a very popular car for GM, low cost, and it worked well. Well, GM said that we had told them we're having trouble transferring it because we want to close down this plant. And GM said, you're not going to close down that plant until you prove you can make that product at the new plant consistently correct. We don't want any problems, which I can understand. Well, to keep this one plant open until they solved it was costing the company $100,000 a month. That's a lot of moolah. And so after about 5 months, and my boss was in charge, he had two research groups. I was in one that I managed, and he was assistant research director. I think he actually had three. And this one was a research group that was outside of Milwaukee, their headquarters at that plant. And after a couple of months, the research director, my boss's boss, called me into his office and said, look, you know, we're having a problem transferring this product over, it's called a coating, to the Toledo plant. And I said, I heard a little about it, but I'm not working in that area. I don't even know anything about coatings. He said, guess what? I want you to solve it. I said, what? I don't know anything about coatings. He said, well, your boss will teach you. And so, well, anyways, it caused a lot of problems because essentially it pointed out my boss didn't know what he was doing. And he didn't. Well, I don't know if he's still even alive, but anyways. So I went to his office, and he had already been told by the research director, I'm getting involved. And he taught me, and there was another chemist there, and they explained how this coating was made and all that. And the problem was they could make it here, but they couldn't make it here. Well, one of the things years earlier, I had a great mentor, Sid Shapiro. And Sid Shapiro is a great chemical engineer who also knew chemistry as well as anybody else, organic chemistry. And to this day, I think I've gotten to the level where I'm almost as sharp as Sid was. And he was a great mentor. He used to always, and at that time, I was in my late 20s and he was already in his almost 70. And he used to beat my head and he used to call me Sonny. And I always say, hey, you're not my father. And we'd laugh. And he'd still call me Sonny. And I'd say, you're still not my father. And we'd laugh more. But he used to beat my head. And one of the bedrocks of things is common sense is not common. Well, common sense would say, you can make it here, but you can't make it here. There's something different going on. What's that difference? Well, nobody bothered to figure that out. How stupid. But anyways, that's why I was brought in. I went to the Milwaukee plant, and I actually had them videotape them making it while I witnessed it and took notes. And I went to the Toledo plant. And guess what? I videotaped what they did, and I also witnessed it. I really didn't have to videotape it, but I was in the mood for overkill, and I sometimes do overkill. And I watched, and immediately I saw the differences. one of the problems was whoever wrote the procedure for the product didn't do a good job of it. When I write a procedure, you try and make it idiot proof so there's no, oh, what do I really do? And one of the problems was they put in warm water you're supposed to use when you make this product. Oh, what's warm water? As soon as I saw that and I'd read the procedure before I went to Milwaukee, what the heck is warm water? I had them while they were filling it, fill a bucket of water, stick a thermometer in there. I saw the temperature. All right, that's the warm water. We went to the other plant. I found out the plant manager to save money decided, oh, we can just put in regular tap water. Well, it was 20 degrees lower and it made a difference. That was one thing. The other thing is at the Milwaukee plant, they used a meter to meter in how much water, which is standard. The plant in Toledo didn't have any meters set up for water meters, which is not that expensive. And they just timed it and assumed they were right. No, you got to be real accurate in codings, I found out. So I told the plant manager, we need a water meter put in this one reactor. He said, that costs money. I said, please do it. And he wouldn't. So I called up the research director, who called up the VP of production, who called up the plant manager, and in no uncertain terms, do what I asked. And they did. And then there was another thing where one company used hydrochloric acid at 28%. It's called a certain Baum. That's the name. They used old name in hydrochloric acid concentration. The other was 32. Well, they didn't change how much acid, they're different concentrations, so they were the same. Well, I changed that, and guess what? If you do the same thing at this plant as this plant, you make the same product. It took them 5 months to have to finally call me in. That was $500,000 wasted. Not good. Now, if I look at the clock, let's take a break now. You're going to get out early today because I cheated and I give lectures when I should have been giving tests. But I think it's better for you to take the test overnight than me saying, turn on your webcams. I'm going to look for anybody cheating. You know, if you want to learn, be honest. And I've trusted you. All right, let's take a break. Come back at 2:50, and I'll see you in about 5 minutes. Time to get going again. All right, everybody back? Welcome back. Now, before I go any further, any questions? Because we're on the home stretch, so hang in there. You made it almost to the end, and you're still breathing and enjoying it, I hope. All right, any questions? My speakers are on, yep. Above my monitor here, I have a shelf. I have 2 computer speakers. They're about like that and that, which means I don't have to wear my hearing aids, which is a good thing. All right, last chapter, yay. And this will not be on test number 4, but it will have some questions on the final. If you think about it, we've talked about 2 of the 3 major food groups, unless you think pizza, beer, wine, and other things are food groups. But anyways, we've talked about fats and oils. We've talked about carbohydrates, and what's missing? Proteins. So let's talk about proteins. Everybody see amino acids, peptides? Thank you. Now, what is amino acid? It's an organic compound that contains both an amino group and a carboxylic acid. And if you notice here, and you've learned about it, we have our carboxylic acid group and amino group. Another way of writing this, which probably helps better, is this. And this is an amino acid, the general form. Did I tell you how lazy organic chemists are and now other chemists? And it really should be an amino carboxylic acid, but that hurts my jaw. So I'm just going to call it an amino acid. And that's what they did. Now, when you have 2 functional groups, and I mentioned it, we're talking about amines, the amino group is considered a substituent amine, and it's called an amino group. And that's how you got the name amino acids. Now, one thing that's very important, here we have a carbonyl carbon, and the carbon attached to the carbonyl carbon, you learned in ketones and aldehyde, is the alpha carbon, and that's still true. All amino acids have the amino group on the alpha carbon. And good news, I'm not going to ask you to learn the names of any amino acids. Well, let's look at a couple right now. All right, thumbs up, people. You see the Wikipedia. Thank you. Boy, I don't even have to say anything. You're already reading my mind. Ooh, that's dangerous. But anyways, here we have a general amino acid, just like I showed you. The alpha carbon has the amino group, and so everybody see on your screen different amino groups. Remember, every bend in a line is a carbon, every end in a line is carbon. And I don't ask you to memorize these, but I just want to show you. If we look at, I don't know, glycine, the simplest amino acid, notice the R group here is a hydrogen. And on the alpha carbon, you have, guess what? An amino group. And if we look at what's another one, serine. Here's your alpha carbon as the amino. You got a carbon with a hydroxyl group. And a whole bunch others. And if we scroll down, let's see, I don't know if I can scroll down. Let me move this out of the way. At the very bottom, you can see phenylalanine. And on the alpha carbon at the very bottom down here, you see an amino group, then a carbon and a benzene ring. So these are all things you've learned this semester. And these are different amino acids. Now, tryptophan, which is this one, which has, if you notice, a heterocyclic compound on what's called the beta carbon, the one attached to the alpha carbon. So they can be very complex. And if you look at cysteine, you can see a sulfur. I'm not sure if it's cysteine or another amino acid with a sulfur in it. Are there any others? I don't know how complete this list is. That's responsible for whether or not you have curly hair or not. You can't tell, but my hair is curly. What's left of it. But anyways, oh, by the way, the grass is always greener. When I was younger and my hair was real curlier, I always wish I had straight hair. And friends of mine who had straight hair wish they had my curly hair. It was interesting. But anyways, these are the amino acids. Now let's look at the alpha carbon right here. What's interesting about that? Well, if R is not a hydrogen, what do you have on that alpha carbon? 4 different groups. And what did you just learn about a carbon with 4 different groups on it, or atoms or combination? It's chiral. Therefore, let's talk about chirality. Remember, this is all test, not going to be on test number 4, but some of it will be on the final. The alpha carbon of amino group is bonded to the 4 different groups when R is not hydrogen. So, except for glycine, which I won't, I don't know what this is. Dr. White is not an amino acid chemist or protein chemist, but if you look at this carbon, has a hydrogen, amino group, methyl, and this carboxylic acid. So this would be a chiral molecule, chiral carbon. Molecules that have chiral carbons are chiral. And therefore, the carbon is chiral, and most amino acids are chiral. And that means amino acids can exist in 2 forms, both right and left. And they do. Now, the following, I'm going to turn the switch off. Will this be on a test or final? Actually, the final. But you might want to know about this for other classes. Now, acid-base properties of amino acids. Amino acids contain an amine, you learned that's a base, and a carboxylic acid, that's an acid. And depending on the pH, it exists where you have this proton right here. And this base, and it transfers acid base, and that's what happened here. Now, if you notice, there are 2 ions in this molecule, and they're not attached to the same atom. The NH3 group is on that carbon, the O- is on the carbonyl. It has a name, zwitterion. And you can tell Dr. White knows it's German because it comes from the German word zwei, which is 2. And a zwitterion has 2 different ions in the same molecule. All molecules have a net zero charge. This, therefore, has a net zero charge. And that's an important property of amino acids. I won't ask this on a test, but for other classes, you may need to know this. Now, a Zwitterion, and I'll never ask this on a test. And by the way, because of my German training, and I also worked in Germany, it's hard for me because I know it's a German word to say it American way, which would be I'll try and get it out. I don't like to say it because it makes my mouth feel funny. Zwitterion. This is Zwitterion. In German, a W is pronounced like we say V. And that's a molecule that has a positive charge on one atom and negative on another, has no net charge. It's Zwitterion. Now, switches on. Let's look at reactions of different amino acids. Now, before I go any further, remember my promise, no new reactions? Well, for test number 3, you learned the following. Take a carboxylic acid and amine. Remember, R prime and R double prime can be hydrogen. And what do you get? An amide. Now, if we come here and, oh, look, isn't it amazing? I've got Technicolor for you. I have in this amino acid a carboxylic acid. I have in this amino acid an amine. And therefore, on this amine, one of the hydrogens is R prime, and this whole thing is your R double prime, or the other way around, and you form an amide bond. So I can react, in this case, two of the same or two different amino acids to form an amide bond and link them together. Now, if we look at this side, I have more amine. Here I have more carboxylic acid, and this can further react with amino acids to form more amide linkages. Everybody with me? And I see someone writing it down, so I'll wait. I'll even have a glass drink of water. Notice no glass, plastic, polyester, a condensation polymer, and this is a thermoplastic polymer. I just gave all the answers away to test 4. No. Now, switches off for this. How many of you have heard of a peptide bond? And a peptide bond, you're going to find out Dr. White's not an amino or protein chemist, is a covalent bond between carboxylic acid of one amino acid and amino group of another. And by my reckoning, a peptide bond is really an amide bond. Why don't they call it a peptide bond? I don't know, but I do. If you go back to this example, what I call an amide bond, this would be a peptide bond. Hope I spelled it right. And I won't ever ask that on a test or the final. This won't be on, but you'll hear that in other classes. And you can raise your hand and ask the instructor, unless you want him to get he or she mad at you, isn't that really an amide bond? The answer is yes. Now, what is a peptide? Switches off here. A peptide is a molecule containing 2 or more amino acids, which the amino acids are joined together. This is Dr. White's writing, a amide bond, but everybody else would call it a peptide bond if you were a protein chemist. Now, why they had to come up with a new name, don't know, but they did. Nobody asked me. I wasn't alive probably when this happened. Now, what's a protein? A protein is a peptide where you have at least 50 amino acids are present connected by amide bonds. I'll never ask on a test what's a protein, but other classes. Now think about that. A protein is a polymer that's a polyamide. It's a lot of let's call it amino acids, this. And they can all be different or similar, and that's what we call a protein. So if I were to take this diamino acid and react this side and this side, so you have a total of 50 of these units in there, that would be a protein. Now it's time for Dr. White to scare you. If you look at your skin, go ahead and touch it. Hopefully it doesn't hurt. Go ahead, come on. You're feeling a polymer of amino acids. Your skin is a protein. My hair, what's left of it, my beard, is also proteins. And those are things that are just polymers of amino acids, natural polymers. Now, what's the functional group that holds the amino acids together in a polymer? And that is an amide. And what did you learn for test number 3? If I take an amide, by the way, the switch is on now. And react it with acid. And now I'm going to use the acid that's actually in your stomach, HCl, and water. And you learned this for test number 3. You get back the carboxylic acid you would have used to make that amide, plus, let me make this a little bigger. Plus the amine salt of the amine you would have used to make that amide. Why? Because, I'll put it up here, amines are basic, and in the presence of acid, you get the amine salt. Well, let's look at when you eat something with protein in it. And when you digest a protein, you consume it, you chew it and swallow it, and it goes in your stomach and intestines and breaks down how? Acid hydrolysis of an amide. And here we have, I wrote it this way, same thing, where R prime and R double prime, one or both can be hydrogens, and acid and water, you get back the carboxylic acid and the amine salt you would have used to make that. Now, I just have a simple peptide, but the same thing is true for all proteins. What's the key linkage? This right here. It's an amide. What did you learn? Or I should better yet, what do you know? So let's look at what happens in your stomach. This part is the carboxylic acid, and this part is, well, actually the nitrogen part. This is this part, this is that. This becomes a carboxylic acid, but this comes along for the ride, but you're in acid and you make the amine salt. So you get this amine salt of this amino acid. And then this part is from here, and you get this amino acid, and this carboxylic acid comes along for the ride. So when you consume a peptide or amino acid, you get back the acid amine salt of that amino acid. And that's how your body breaks down. Now, one of the most important things, as I've said a number of times this semester, you know what I'm going to say about Mother Nature now. Who's the greatest organic chemist around? Mother Nature. And notice in this one reaction, what has she done? She's made an amino acid that has a charge on it. It's now polar, and polar makes it more water soluble in your stomach and your blood. Think about that. Isn't that amazing? Well, I'm a chemist. I think of things like that, and I'm easily amazed. And that's that. Oh, no, I think we're done. Not yet. All right, couple of things. First of all, I don't know if I mentioned it, your enzymes are really catalysts. If I react a lot of amino acids together, what do I get? A protein. And if I take a protein, and I'll just generalize it, acid plus water, and really I'm just going to put it down simple. I won't do the amine salt. You get back amino acids, actually the amine salt of amino acids. And that's how your body breaks down protein. So think about it. Your body puts together amino acids to make protein for various things in our body. And now I'm well beyond my knowledge of the human body, but I think, aren't muscles made of protein? Which means your heart is made of protein, because that's a big muscle, I think. My cardiologist told me that. And that's how your body makes it. Now, when you eat something, now, if you like animal protein, if you had a hot dog, hamburger, or a nice steak, that's how your body breaks it down. If you're a vegetarian, which I think nowadays is called vegan, I always wonder if you're a vegan, are you from Venus? But never mind. That's a bad joke. But if you're a vegetarian, my sister was for a number of years, and she decided, no, I'd like to eat meat once in a while, but mostly she's vegetarian. If you have soybeans or things like that, lentils, all of them contain a lot of protein. Now, switches on full time. Let's do the following. Leaving my class, you should know how to describe the three major food groups with words and general reaction, what happens when you eat it. I've just gone through fats and oils, carbohydrates, and now let's talk about when you eat a protein or something with protein in it. What's the functional group in a protein? And that's an amide, is the key functional group. That's what holds amino acids together. Switches on up to 1,000 now. Ooh, got everybody's attention. And next, what's the general reaction? How do you describe that with words? And that's acid hydrolysis of an amide, because that's the key functional group holding the amino acids together in a protein. And what's the general reaction? And for this, so you know the counter ion, let's use hydrochloric acid. And for test 3, you learn this stuff. And you get back the carboxylic acid you would have used to make that amide, plus the amine salt that you would have used to make that amide. Now, it just so happens in a amino acid, these two are connected. And now you've learned about organic chemistry. And Dr. White, what I've been telling you, my world of organic chemistry is your world of organic chemistry. And now you know a lot about it, more than most Americans or people on this planet. Doesn't that make you feel good? Everybody say, yes, Dr. White. No, you don't have to. And with that, let me remind you tonight, office hours. Don't forget, Wednesday is the deadline for the extra credit project if you want to do it. And I'm done. We'll have our lab on Wednesday. Like I said, I sold a couple hours from you because I didn't give tests during our actual lecture time. But I think that worked out better for you too. With that, I'll stick around if anybody has any last minute questions. Other than that, gehen gesund, be healthy. Goodbye. Ooh.